Okay, Assalamualaikum and hello everyone. This is Guru P3 and the title of this presentation is about tree properties. So for the first part of the video is going to be about the experiment, the procedure itself, and then the next part is the results and discussion.
Okay, so for safety, I'm going to talk before the test first. So ensure that before the test, you have the correct grips and the specimen is in the correct dimension. Next, make sure that you wear the proper attire, which is the lab coat, closed shoes, and during conducting an experiment, wear glasses. And lastly, ensure that the emergency button is working properly. Okay, so during the test, make sure that you do not leave the machine unattended. And next, you do not interfere with the specimen during the load is applied. Okay, so for the last part, which is after the test, make sure that the experiment fully stops, so no more load is applied from the machine. And after that, remove the specimen carefully from the machine. And last but not least, do not forget to close the machine after your use.
Okay, so for now, this is the anatomy of the machine. So we got two pillars right here, and a moving crosshead, and the base plate. All of this is to ensure that the machine or the load applied to the sample is coaxial, which means that the load is only being applied to the z-axis, which means that it only goes up and down. It does not go front and back, left or right, or twist around. So for the next part is the emergency stop button. So this is to ensure that machine stops whenever something bad happens. It could be anything. And for the next part is the vertical positioning button. It allows the moving crosshead or the top jig to actually move and up and down in order to actually position the sample to the right place. Okay, so for now, for the next part, which is other than the machine, we got a workstation PC. So this is where you input all the dimensions of the sample, somewhat like thickness, height, gauge length, whatever. And after that, you do the test and you can get data or any graph relating to creep. Let's say a graph of displacement against time, and that's about it.
For the methodology, firstly, you need to create your own sample. We can create the sample by using the previous sample and use it as the base to sketch the other sample. You can sketch it by using the marker pen or any useful equipment. After you sketch it, you need to cut it so it was the shape of the previous sample using scissors. After that, you need to measure all the important lengths such as length, thickness, and the initial gauge. This is important because when you input the wrong number, it will show a wrong result at the experiment. Next, we're gonna run the experiment. To run it, firstly, we're gonna take our sample and put it on the machine. To put it, make sure that the edge of the sample was held tightly on the grip. Also, you're gonna make sure that the sample was at the 90 degrees so that the result was better. Next, we're gonna pull the machine down. After that, we are going to tighten the grip so the sample does not move during the experiment. After you put the sample on the upper grip, you're gonna make sure you click the zero displacement button so that the displacement was a valid value. So we click that. After that, we're going to grip the bottom of the sample. After you grip the bottom sample, we are going to balance the force. After that, we are going to input our specimen dimension such as width, thickness and length. After we input the dimension, we are going to run the test. The test was going to measure all the grid properties during the experiment. After the test, the specimen will snap into two pieces, and then we are going to need to measure the length, width and the thickness after the test.
For this grid test, several measurements and results were recorded throughout the experiment. First, the dimension of specimen were measured before testing. For specimen number 4, the initial gauge length was 50 mm, the width was 12.85 mm, and the thickness was 0.07 mm. During the test, a constant tensile force of 0.147 kN was applied to the specimen. The main data recorded during the experiment were time and elongation. Measurements were taken at every 5 seconds. At 5 seconds, the elongation was recorded as 5.161 mm. As the test continued, the elongation gradually increased. At 300 seconds, the elongation reached 7.9992 mm, and at the end of the test, which was 590 seconds, the elongation increased to 8.2663 mm. Using the elongation value, the strain was calculated by dividing the elongation by the initial gauge length of 50 mm. Epsilon equals to delta L over L. For example, at 5 seconds, the strain was 0.1032 mm per millimeter. At 300 seconds, the strain increased at 0.16 mm per millimeter, and at 590 seconds, the final strain was 0.1653 mm per millimeter. Another important result recorded was the final gauge length of the specimen after testing. The length increased from 50 mm to 58.2663 mm, giving total permanent elongation of 8.2663 mm. Therefore, the main result measured and recorded in this experiment were the specimen dimension, applied force, elongation over time, strain values, and the final length of the specimen after grid deformation.
The graph on the top left is the expected results for plastics. Meanwhile, the graph on the top right is our actual results. The reason it is so different is because the graph on the left goes through all three stages of creep: primary, secondary, and tertiary, where in tertiary creep, the strain rate increases rapidly and rupture happens. In our experiment, we did not go through rupture, which means we did not go through the tertiary stage of creep. We only went through primary and secondary. Another reason is load. In the first graph, the load used is much higher compared to our load, which is 147 newtons. If a much similar load was used, we would the expected results and our actual results would look much more similar. For the graph itself, we can use a tool like Desmos. To input our strain and time data, where time is the x-axis and the strain is the y-axis.